So for our final set, our final three reactions that are going to focus on electrophilic addition, they really didn't fit into any theme. So this is kind of just a grab bag of what's left. The first one we're going to talk about a catalytic hydrogenation. So this is going to be a way to add multiple hydrogens. You can do this in a variety of ways. In short, you're going to be using H2 gas. So this is going to be hydrogen. And you're going to be bubbling H2 gas into a reaction mixture that includes a catalyst. Your catalyst is going to be a metal. Platinum, palladium, and nickel are some of the most common ones. There's probably a few others that also work, but platinum, palladium, and nickel are some of the most common. Most of the time when I do hydrogenation reactions in the lab, I use palladium on carbon. That's just supported to play around with surface area, and then hydrogen gas. Now this is going to be a syn addition of two H's, so it's going to be kind of going from a kind of like point of unsaturated to be fully saturated. And the way this works is you're going to have your metal. So here's just my generic metal, like platinum, and on the surface of platinum, you're going to have a bunch of hydrogens. Now, the core of most of the time, these could be like little nanoparticles, for example. The core of your platinum is platinum, and it's just the surface that's going to have a bunch of your H's. And then what you're going to do is you're going to kind of have your double bond, and your double bond is going to kind of almost act like a UFO coming down to like kidnap a cow. Super odd example, but I've always wanted to like make artwork that has like a UFO as a double bond coming down to steal hydrogens instead of cows, but eventually I'll have time to do it. Super distracted there, sorry. So you'll have your double bond, and what's going to happen is your double bond is going to come down, it's going to dock, and as it docks, it's going to interact with multiple hydrogens. So it's going to kind of come down, and then two H's are going to be added on the same side, and then it's going to leave. And you're going to keep having this occur again and again and again. And you'll have extra H2 to generate any vacancies on your catalyst. And this process will just keep going until you finish. In practicality, these reactions are very interesting. Normally for hydrogen gas, you'll normally actually have a physical balloon, like a birthday balloon, that you'll actually fill with hydrogen gas. And then you'll actually have that with a long needle actually going into your reaction flask, and then kind of slowly be bubbling hydrogen in. When you have a double bond, any protons that are on it are going to be pretty noticeable on NMR, way out in like your vinyl region of like 5 to 6. So you can actually do real-time monitoring with NMR, where you're actually tracking this reaction as you go. They can be a kind of a pain in the ass sometimes because your catalyst can go bad pretty easily, and you might need to regenerate it. And most of the time when I did this, I would actually go from a triple bond all the way down to a single bond, so I had to do even more chemistry. But they're fun. You get a bunch of balloons of hydrogen in your fume hood. So this is going to be our kind of catalytic hydrogenation. H2 plus a metal, and then this is going to be a syn addition or a same side addition of your two hydrogens. And that's kind of one of our first kind of random grab bags. That's going to be a way just going from a double bond to a single bond. Our next kind of grab bag of reactions is going to be focused on a halohydrin. We briefly mentioned that there is such a thing as a halohydrin in the last video when we were talking about making epoxides. However, let's go and talk about how we actually make halohydrins. So halohydrins are going to be reactions where you can take a double bond and you can add one halogen and one alcohol. We've now individually talked about ways where you can add alcohols and you can add halogens, but there's also a technique where you can add both of them at the same time. And this is going to follow a Markovnikov with an anti-addition type of reaction. So in this, we are going to do, so in your halohydrin formation, we are going to be using a halogen, so like Br2, and then water. Now, when you have a double bond and something like a Br2, you can go forward and form a bromonium ion. And we've actually seen that previously. where you can do this kind of cyclization and then kicking out your leaving group, and that's going to form your bromonium ion. Normally, when you do a reaction that doesn't have any water or a solvent that's going to interact with anything, you'll have that bromine do a backside attack and then open up to form your anti-addition of your 2 halogens. If, however, though, you add a bunch of water, that water is actually going to preferentially open rather than your bromine, mostly because your water is going to surround that negative charge, and it's going to make it really hard for that bromine to come and attack. It's kind of almost like using, like, if you think of like an SN2 reaction. In SN2 reactions, you don't want to have a protic solvent because you don't want to surround your nucleophile. Here, if you use water, that's going to surround and kind of stop that attack, and instead water is going to open up, and that's where we're going to get our OH. So for our mechanism, I'm already going to kind of start with our bromonium ion because we've already kind of shown how to make it. So if we have our bromonium ion, and then we'll have our water. And there is going to be bromine ions, which are going to be here, but they're going to be surrounded by a bunch of water that's going to be kind of blocking them off. So it's not able to do some attacking. And that's why we add a protic solvent like water. Now this is going to attack and open up our bromonium the exact same as we would show before. So this is going to attack on the more substituted side to give the more stable transition state. And because of the fact that we are doing a backside attack there, that's going to be an anti-addition of a Br, and then you'll have your oxonium. And then what you'll do is you'll have, for example, more water that can come and deprotonate you to then give you your final product, which is going to be your Br and your OH. And here we're going to see that we're going to add our bromine on the side of our hydrogens, or you treat bromine like you would a hydrogen. It's going to go on the more or the less substituted side, where your alcohol is going to go on your more substituted side. Key difference between your normal bromination, for example, and your halohydrin formation is going to be the inclusion of water, and that water is going to open up your bromonium rather than your halogen. This is going to form an anti-attack because these are on the opposite side. So an anti-attack. And this is going to follow technically Markovnikov's rule. So this does follow Markovnikov's. When we're thinking about our Markovnikovs, you can almost think treat your H and your X. I was going to write bromine. Your H and your X you can kind of treat as the same. And then your alcohol is going to be added to the more substituted side. And that's going to be your halohydrin formation. So Br2 and water rather than just Br2. If you just do Br2, you add 2 bromines. If you do Br2 and water, you add a bromine and an alcohol. And then once you form that halohydrin, you can do more chemistry. For example, if you expose it to a base, you can make an epoxide, and you can do a variety of other chemistry. Now, the very last reaction that we're going to talk about is going to be actually cleaving or breaking our double bonds altogether. And there are going to be 2 types of reactions that we're going to do for this. And these are broadly going to be classified as ozonolysis reactions because they're going to use ozone. You could also do a similar reaction with permanganate, so that KMNO4. If you remember, that KMNO4 was that same chemical that could do the di-alcohol addition with a syn side. If you warm it up, you can actually cleave bonds. So in these conditions, what we're going to be doing is we are going to be breaking our double bond. And as we break that double bond, we're going to be adding a bunch of oxygen species. So this is going to be an oxidation. The key difference between our ozone and our permanganate is going to be what happens to points of saturation. So if you have a hydrogen and you react with this with ozone, it is a gentler oxidation. So you can actually keep your hydrogen there and you'll generate an aldehyde. In your permanganate, that's actually a really strong oxidizer. So it's actually going to turn that hydrogen into an alcohol as well. So anything it touches, it turns to a oxygen-like species. So key difference between these two conditions, the ozone versus your KMNO4. Your CH is going to survive in your ozonolysis, and it's going to become an aldehyde. If you use KMNO4, your CH is not going to survive. It's going to oxidize into a carboxylic acid. Now, the actual mechanism of this is maybe a little bit complex. I'm going to show just a little bit of what's actually happening. So much like how in our osmium, you kind of get a species that's going to come and dock on a face of your double bond. Your ozone is actually going to do something pretty similar. So you're going to have your double bond, and then it's actually going to form a 5-membered ring with the ozone rather than with your osmium. So pretty similar to what happened in the last mechanism. Same arrows and kind of pushing things too. This species is it's described as a mole ozonide. And when this breaks down, what you're going to do is you're going to have your bonds kind of all jump over by one, and that's going to give you your oxidation and breaking the bond, which would be right here, and give you a double bond and a double bond at those two spots. So if you want to break a double bond and you want to save any hydrogens, you can use a ozonolysis reaction. If you want to just oxidize everything, you can use permanganate in warm conditions. And those are going to be the kind of last two reactions where we're talking about bonds breaking. And that is our kind of fire hose of all kinds of different reactions. I have a summary, and actually we'll do the summary in our next video. We'll do one short video that's kind of walking through kind of a summary. So that gives us our ways to add two H's, which is going to be a hydrogenation. Most of the time it's catalytic. We talked about halohydrins and then ways to break bonds in this video.